Good evening. Today is lecture 7. We will be learning about MOSFET small signal analysis on the 20th of September. We will start with understanding what is small signal and where it is going to be used. So let's begin. So in the previous classes, we have identified what is DC signal and what is a small signal. In the bias curve, you would have seen that for a given object, we have used a DC signal and a small signal around it. And that small signal tends to be 1/10 or 1/20th the factor. That is the number that we have gone ahead with. So now we will understand what that 1/20th or 1/10 is important in the analysis. And this comes directly for two things. One, it appears in saturation region. Okay, and everybody is expected to be familiar with the input-output characteristics of a transistor. In this case, I am drawing a NMOS device whose output looks as follows. And let us quickly summarize the areas of importance. So this is going to be the cutoff. This is triode. And this is the linear operation. Sorry, this is saturation. My apologies. In this case, you will define the point where there is maximum gain observed on both points. And that point is what you call your DC operating point, which is going to be operational for most calculations that we will do. This dotted line will define the values V in, V out, which defines the DC operating point for which you operate, voltage in and voltage out. And this is designed or defined here for an NMOS device. It is the almost opposite for the PMOS device. Now, what do we understand that where a system is in saturation? When the system is in saturation, the first thing you understand is what is the drain current. What is the drain current given? Now let us pay attention to the notation. When you are talking about V spade, that small I with capital letter informs. So in this case, let us revise. This is the total current. This is going to be the DC current given in capital letters. This is the AC current given in small letters. So this is the notation that we will consistently follow. This is similar with the voltage also. So for voltage, it will be V capital D is equal to V large D minus small v small d. That will be the notation for voltage. Right? Now that you have understood, let us deep dive. What does the current inform here? What is the drain current? Drain current is ID is equal to mu n Cox W by L, half mu n Cox W by L, here represented as K. Henceforth, this will be the notation that we will follow. W by L is half mu n Cox W by L, you will call it as K. Then you have VGS minus VT the whole square. This VGS is written as capital V with capital GS, small v with small gs minus VT, which is again capital, given the whole square. Now, What do you identify from this term? You can consider this as a variable, VGS, and these two to be the constant. And now you can find out what is the equation. Expand this equation. So that would be VGS minus VT, the whole square, plus, right? No. VGS minus VT over plus VGS. So plus this is 2 times VGS minus VT multiplied by VGS plus VGS whole square. Each of them multiplied by K. Now what does this notify here? This factor is called I capital D. This factor is called small id. And what is this VGS square? This VGS call is the AC value, right? It is a very, very small value. So what is this AC value? So what is we define it as small? It is very small if VGS is very small compared to this factor, that is less than capital VGS minus VT times 2. Why did we get this? When we take 2 times VGS minus VT into VGS and equate it to the VGS whole square, one VGS gets common, and then we define small VGS is very small compared to 2 times VGS minus VT. Okay. Now this is what we consider or call as small signal condition. All our analysis are relative to this condition. VGS is very less compared to 2 times VGS minus VT. This is called a small signal condition. Now, once you eliminate this, what is left over? Your ID, look at my notation now. ID is 2 times K times VGS minus VT times VGS. Now, what does that give you? If you take out ID by VGS, which will give you your transconductance. GM is ID over VGS is equal to 2 times K VGS VGS minus VT. Now, this is called small signal transconductance, properly defined. Small signal transconductance. Right? Or this value is also called as overdrive voltage, which is VGS minus VT is called overdrive. What does that mean? You are driving when VGS is equal to VT, right? You are in the correct threshold. As you increase the VGS value, it is putting the transistor into an overdrive mode. You're driving it more. That is why this is called overdrive voltage, and it is how much the VGS is greater than VT. So that will be your overdrive voltage, right? Or the way to define this, you can do that definition is GM is equal to 2K times V overdrive. So this is another terminology that will be commonly used in analog design, especially with transistor design, where overdrive voltage is defined. Now, how can you derive this GM factor? The formal way of deriving the GM factor is start with the equation. Differential of I capital D, that is this equation, divided by VGS value. The VGS. Now there has to be something common, right? That common is small v capital GS is equal to capital GS. That means VGS is negligible. That is small signal, right? Extremely small. That will be the condition of this. And for that, you will get this equation 2K times VGS is a factor, right? 2K times VGS minus VT. V capital GS. VGS minus VT, where you are defining V capital GS is equal to VGS. And that is a function of, what is that a function of? That is a function of VGS. So here this becomes VGS. So this equation is what you will use to derive. Okay. I'm going a little slow because this is important information. Now, once you have this, what do you get? Your ID, small ID, right? That we are using here. This small ID is given as 2K times V, capital V, GS minus VT, VGS. Now, this is defined as ID equal to GM VGS. So, this is also going to be a common equation that you are going to use in small signal analysis, which is the current topic that we are going to look ahead. So, current multiplied by the trans is equal to transconductance multiplied by the differential voltage across it. Right? Now, what is the physical meaning of this? Physical meaning is, if there is a small VGS change, you will see a large ID or a change in the drain current, or any change in VGS or a small change in VGS will give rise to a small change in ID. This is the factor. But this is directly dependent on the bias point that you have defined here. What is going to be the DC bias point for the VGS and ID? So depending upon that, you will define. And now what is this GM? GM is going to be the slope of the ID VGS curve. So if you have a curve which is the I and ID and the VGS curve, and the curve graph that you would see comes like this, not this graph. So as your VGS increases, your drain current will increase. So as you get this curve, if you define the DC point over here, the slope at this point the tangent or the slope that you see at this point is given as your GM value. So that shows what is the slope that you see, and you will understand what is the amount of VGS that you apply and the current you get. For example, if you apply a VGS in this range, right, then the current output will vary between these two terms. So this will be ID, this will be VGS. So this is the ID VGS curve. This is very similar to the diode knee voltage that you see and the current flowing through the diode. So similar you will see for the transistor also. So that will be the starting point of the small signal voltage. Now let us take an example and see how that is applied. And this will be the same equation that we used before, where we used the transistor as a switch or an amplifier example. This is the equation that we used, and in this case, we will apply a voltage. We will apply two different voltages. This is capital V, capital G. This is a DC voltage. And this is a small AC voltage, small VGS. And this is applied at the input, and this value plus minus reference to the ground is given as small v, capital GS, indicating both DC and AC component. Next, this resistor is only DC, so the current that will flow is directly dependent on what is the VD voltage and VGS voltage. So this will be small I, capital D. Here you will have the supply voltage VDD, and the output given here is given as VD, small v, capital D. So this is the equation. Now, what are the total drain voltages or any instantaneous drain voltage? The instantaneous drain voltage is given as VDS is equal to, in this case, it is VD. So VD is taken across this way. So VD is equal to VDS is equal to V capital D is equal to VDD. This is a DC voltage multiplied by AC plus DC current and DC voltage. So ID RD. Note the notation, small I, capital D. That means there is both AC and DC component here. Right? Now, if you expand that, VDD minus ID is I capital D plus I small d multiplied by R capital D. Now, if you, in this case, if you take up or club all the DC components together, VDD minus IDRD, I capital ID minus small id capital RD. Now, this is the small signal condition equal to VD. What does this give? In this case, here is the large signal component and this is the small signal component. So this is the small signal component of drain voltage. Small signal component of VD. So this is what you will have to understand. Now, since this is the small signal variant, what do you get is the total impedance VD equal to minus ID R capital D. Now, ID, small id from the previous is given as ID equal to GM VGS. Now, this can be rewritten as minus GM VGS times RD. What do you do with this one? How is this useful? It is useful because now you are going to define something called the gain. What is the gain? VGS is your input, VD is your output. Right? This is your input, this is your output. And if you notice, both are voltage. So now we will define something called the small signal voltage gain, which is given as or noted as AV equal to output over the input, VD over VGS is given as minus GM RD. Right? Now, this particular condition shows that when a transistor is connected in this configuration, the gain changes. Right? The input becomes inverted in the output. Note the signal change, sign change here. And the absolute gain is given as the GM of this transistor multiplied by the load resistance present. So this is called your small signal voltage gain. Henceforth, we will only refer to as voltage gain. The small signal will be implicit in our discussion. So now we have defined the transconductance. We have defined small signal voltage gain. Now, what will happen if the small signal voltage gain is large or small? small signal voltage gain will come, or a gain is coming. When do you get gain? When it is greater than the input. Output is greater than the input. How do we define output is greater than the input? That minus GMRD, or in this case, just GMRD. If it is very large compared to 1, then we call it as a small signal voltage gain. Now, another observation that we spoke, AV is equal to minus GMRD. So this is the reference equation. So what all information can you gain? First one, GMRD is very large compared to 1. Second, there is a VD is 180-degree phase shifted. 180-degree phase shifted to VGS. So there is a signal inversion. Signal inversion. Okay. All no. This is again under the assumption. What is the assumption that we will always follow? 2VGS minus VT is very large compared to VGS. So this is the assumption condition in saturation that we are following. That's right. So for saturation, what is the other observation that we will see from this figure? That VD minimum will be greater than VG maximum minus VT. What is VD maximum? The supply voltage. So VD max will be less than or equal to the total supply voltage. So this will be the operation that we will understand. Any questions? Now we will go into defining the small signal modeling. This is an important part. You will be using small signal modeling extensively in your studies, whether it is analog, whether it is digital, whether it is RF. You will see small signal analysis coming into the picture. Let us now construct the small signal model. How do you replace? So let us use the same figure from before to help the construction, but we will write it a little smaller. VDD, RD, I capital D, small VGS, capital VGS. This is your VT, right? VGS minus VT. Now, what are the definitions that we know? The current in the gate will be 0. There is no current flow in the gate. Always remember. So this will be an important factor. Now, let us replace this transistor with a small signal model. So how do you replace the transistor? We will do it as follows. From the various equations that we found, we will do. So let us define a small box first. Y box, because this is the easiest way to understand. 3-terminal device. What are the 3 terminals of the device? This is your gate. This is your drain. This is your source. Now, why have I done this? Because this is called a common source configuration of using a transistor. What does this mean? The source is common between the input and the output. Here, what is your output? Your output V0. This is your input V in. So what is the common? Here it is. Input is measured to the ground here from VGS. Output is measured to ground here to VDS. So VDS, VGS, is here. So that is why this is a common source configuration, and we have just used that terminology like this. This is also called T model. Why? Because it is representative of a T. So let us continue. So what is the current going into G? Current going into G is 0. Ig is 0. What is the current going into D? Right? It is going into drain. This drain is given as small I, capital D. Correct? No, it is not, because it is small signal model. It is only small d. You will not consider VGS, VDS, I capital. All caps will not be considered in small signal model. So these are do not use. Everything is going to be small notation. So this is IG. Right? So IG is 0. ID is whatever is going to flow here. Now, what is the output? What is the output that we found? VD is minus GM VGS times RD. So VD will be GM VGS. So what is GM VGS? GM VGS is this is a current factor, right? Notation is right. So VD is equal to minus GM VGS times RD. So GM VGS effectively has the notation of a current. V is equal to I into R. So since the same drain current flows inside, this is a current. What is this current? It is a voltage controlled current device, right? Or a voltage controlled current source. This is a current source, right? So current typically is written as C. Pardon me for writing I. So it becomes voltage controlled current source, VCCS. And this value of VCCS is given as, what is it given as? GM VGS. No, this is now connected to the ground. So the drain current, whatever is flowing, will flow out through the source. So whatever current flows in the drain will also flow out to the source. So that is a common rule that you will follow. Common rule, IG is 0. Second, drain current flows from drain to source and there is no loss. So these are, understand this. So the same drain current which is going, flowing out. Now the source is common to drain and source, right? So this is the common point. So this is the common negative point for both. This will be the common positive point for both. Now what is this value? This value is the voltage, potential difference VGS applied between the gate and the source. So what this means, the whatever is the potential applied at the VGS, that multiplied by the transconductance gives result to the drain current flow flowing to the drain. Okay. Now this is the T model. Now what will happen to the equivalent T model with channel modulation? Till now we have assumed there is no channel modulation. So what will happen with channel modulation? With channel modulation, you will see what is the circuit, where the modulation present, gate to source or gate to drain, right? There is a channel modulation between drain to source, that is here. Channel is between drain and source only, right? So you will see a small resistance here called R0. So that resistance will come as shown here. How is it shown? First is your GM VGS. This is GM VGS, and this node, you will see gate. I don't know. What is it? Then you will see a R0 from drain to source. This will be R0. Now, what is this R0 here? Don't know, right? This is the output resistance. Output resistance. Okay. Last topic, and I will close in 5 minutes. R0 resistance is will be defined as, so this will be your total output here. This is your source terminal, and here you will have the VGS. The gate. So this is the effective resistance that you see, which is due to the channel modulation. So what is the total ID that you will get here? So there is a drain current coming from here, right? So ID is getting split into two parts now. So one going here, another going here. Now, how do you identify what is this value? There is an equation. So the total ID that is flowing here and the total ID that flows here. So the Kirchhoff current law says total ID is GM VGS, that is this value, plus voltage. Voltage between these two resistances is D to S, VDS by R0. So VDS by R0 is going to be the actual drain current with channel length modulation. Now, channel length modulation, you can equate, if you remember, is K times V GS minus VT the whole square times 1 plus lambda V capital DS. Right. So this is going to be the capital VDS. Now, how do you derive it? How do you define a relationship between these two? In the transconductance, you know, ID is GM-VGS. We just spoke about it. That is small signal value. But when there is channel length modulation taken into consideration, you will multiply this with add a VDS by R0 factor. And this is dependent from the ID that is flowing. So if you look at the commonality between these two parts of this equation, VDS by R0, lambda VDS, and its relationship to ID, you will get it as, just if you equate them, you will see that ID is given as VDS by R0, this ID here. Now this R0 is defined as output resistance. What is the output resistance? R0 is equal to 1 over lambda times K, using this value, lambda times K, VGS minus VT the whole square. Multiply, you just lambda times K, VGS minus VT the whole square times VDS. So that is goes there. Now, what does this relationship look like? This relationship typically looks like R0 over 1 over lambda times K times VGS minus VT whole square is ID. So this is another relationship of output resistance with the drain current that we follow. Remember, the small signal current that you will do in most analysis is you will use ID is GM over GM times VGS plus VDS minus R0. So this is the equivalent representation that you will see and understand. Now, let me close here. Next class, that is tomorrow, we will learn about, rather than tomorrow, let me just post the next class. Next class, we will do a complete DC analysis with an example, right? We will always do this like we did in the previous session. Okay, class, thank you. And before we go, please join in for the customary photograph session. I am seeing some new people today. My typical video length is lesser. 1, 2, 3, 5, 10, 15, 18. Okay, 22 enrolled, but only 18 in class. Okay, few more to go. Hemant, Sai Charan, Srujan, Trinath. So your alumni are waiting for you badly. So let me take a quick photograph and go. So smiling faces, everybody. One, two, three. Smile. Okay, class, that's good. I got some candid photographs, looks like. So hope this is okay with all of you. Kartike has a very good smile. Farah is like, okay, I missed it. One more photo, just so that I make good sense of all of you, because this is good. And by the way, for people who are interested, I have uploaded all these videos on YouTube. So you can use this YouTube when you're traveling by bus, going any revision you want to do, you can do it. Okay, I will share the link with you all so that now you can revise whenever you have time, or whenever you are in between your social media visits. You can use the same YouTube videos to quickly browse through, and your exam preparation also can be a little easier, because you don't have to have textbook. Whenever you're walking, driving, keep your wireless headset, keep your music, whatever, continue going with your work.